Hello everyone. Today I will present my homework about the PID controller. Let's start with the base code. The nature of PID controller. First, what is PID controller? It's an automatic control tool that works by correcting errors. Its core idea is simple. Compare the send byte and the process value. Then change the output to make the error smaller. Let me give you a daily example. Adjusting the water temperature of a faucet. Suppose you want warm water, but the correct water is cold. You check the gap and turn the faucet towards hot water. This is electrically how PID works. Set byte, find error, adjust output, change process value. Now let's talk about the first game, KP. The proportional gain, its rules is the bigger the error, the stronger the output adjustment. The output is directly linked to the error. Take the water temperature example again. Target 40 temperature. Correct is 30. KP is 0.5. The adjustment we need is 10 and 0.5 is 5. So we turn the faucet 5 to hot. If the error becomes 5 later, the adjustment becomes 2.5. But there's a catch. A bigger KP makes the system adjust faster, but it can easily cause overshot, like if the water gets hotter than 40. Next is KI. The integral gain. Its job is to fix the state error that KP alone can't solve. Standard state error is when the process value stops just short of the set point, even after KP adjusts. Let's go back to the water after using KP. The water stays at 38 below the target. Let's say Ki is 0.2 and this 2 error lasts for 3 seconds. The integral output is 2 and 3 seconds and 0.2 is 1.2. We add this 1.2 to the KP output, and little by little, the 2 error disappeared. A bigger KI fix the standard state error faster, but it can make the system like the water temperature going up and down repeatedly. The third gate is KD. The derivative gate is like a predictor. It adjusts in advance based on how fast the error is changing to stop overshot. Imagine the water temperature rises quickly from 30 to 38 in 1 second. the error drops from 10 to 2. That's a fast change. Let's take KD is 0.3. The derivative output looks at this fast drop and calculate is 2.4. This means we reduce the hot water input in advance, so the water doesn't go over 40. A bigger KD makes the prediction stronger, but it's too sensitive to small change. Like if the water temperature jump 1 for a second, KD might misjudge it as a big turd. Now let's look at how these three gains work together. The core formula for PID output is this. Let's break this down simply. UT, the controller output, like how much hot water to let through or how much power a motor use. ET, the error. TI, the integral time constant. Bigger Ki means smaller Ti. TD, the derivative time constant. Bigger KD means bigger TD. The key point here is PID don't work alone. They work together to adjust the output. It's not just adding their output one by one. To check if a PID system works well, we use performance indicators. First is rest time, TR. It's the time the system takes to go from low to near the set point. If there's no overshot, TR is the time from 0% to 100% of the set point. If there is overshot, TR is from 10% to 90% of the set point. Example, pouring 100 of water into a cup, set point is 100. Shorter TR means the system responds faster, like using a cup with a bigger mouth. You pour water faster, so TR is shorter. Next are two more indicators, peak times and overshot. First peak time is the time the system takes to reach its first peak after overshooting. Example, when pouring water, you overshot and get 120. If it takes 4 seconds to reach 120 from the start, TP is 4 seconds. TP tells us how fast the system second overshot. It's a percentage that shows how much the system goes over the set point. The formula is this using the water example like this. The last two is setting time and steady state error. Setting time is the shortest time the system takes to stay within a small error range and never go out again. Example, the water level stabilizes between 98 and 102 and stay there. If it takes 8 seconds to get there from the start, TS is 8 seconds. TS shows how fast the system becomes stable. ESS is the error left after the system is full stable. Example, if you only use P control, no I or D, the water stabilizes at 98. ESS is 2. With full PID control, it stabilizes at 100. ESS then is 0. ESS shows how accurate the system is. Now let's look at real uses of PID. First, linear control. This is when the system's output and input have a straight line relationship, and the controlled object moves in a straight line, like speed or position. A common example is an express shorting cover belt. The control target is to keep the belt speed at 0.5, but there's a problem. When more heavy packages are on the belt, the speed drops to 0.4. That's an error of 0.1, and PID helps fix this. Let's work through how PID adjusts the conveyor belt. 1. KP works first. KP is 2. The output is 0.1 and 2, so is 0.2. So the belt speed goes from 0.4 up to 0.6. That's overshot. Then KD is 0.5. It detects the speed is rising fast, so it offsets 0.1 of the output. Now the speed drops to 0.55. 3. Finally, KI fixes the small error. The error is now 0.05 and it lasts 5 seconds. KI is 0.1, so the integer output is 0.05 and 5 and 0.1, so is 0.025. We add this, so the speed drops to 0.5. Result: the conveyor belt stays at 0.5, so express package is sorted accurately. The second application is rotation control. The system controls rotation, like rotation angle, angular velocity, or rotation speed. The control objects are things like motors or propellers. A good example is a UAV propels The control target is to keep the propel speed at 1 million RPM. This keeps the UAV hovering at 10 meters, but if a gust of wind hits, the propel slows down to 900 RPM. The error is 100 RPM, so the UAV starts to descend and PID steps in. Let's see the adjustment process. KP starts. KP is 0.3. Output is 100 RPM and multiply 0.3, so is 30 RPM. The propelling speed goes from 900 RPM up to 1030 RPM overshot. KD adjust. KD is 0.2. It seems the speed rising fast, so it offsets 26 RPM. Now the speed drops to 1004 RPM. KI fix the last error. The error is 4 RPM and it lasts 4 seconds. KI is 0.05, so integral output is 0.8 RPM at this, and the speed drops to 1 million RPM. Result, the UAV goes back to hovering at 10 meters and feels stably. To wrap up, let's memory the key point. PID crew, P adjust in real time. I eliminated stable state error. D expresses overshot. All three work by correcting errors. Performance indicators TR, TP, TS, ESS 3. Application difference, linger control, and rotational control use the same PID logical, but we need to adjust the KP, KI, KD for each scroll. That's the end of my pro sentence. Thank you for your listening. This is my or answer. Goodbye.